Let's go through an interesting example of an electrophilic aromatic substitution discussion question. So shown here is a nitration reaction, and notice that there's actually a minor product that is a dinitration product. And there's two questions here. First, explain the observed regiochemistry of the minor nitration product. So why does the nitro group go to the position that it does? And there's a hint. Notice we have acidic reaction conditions. And then the second question is, of all the possible dinitration products, only one is observed. So can you propose a structure for the dinitration product and explain why that is the only one expected to form? So before we get going solving this, let's take a look at these two questions as clicker questions. Okay, so let's go through and solve this problem. So the hint says that we have acidic reaction conditions, and what happens when we have acidic reaction conditions? Well, something's going to get protonated. And the thing that's going to get protonated is this carbonyl group. And when we protonate the carbonyl group, we get an interesting intermediate. So we would expect that under acidic conditions, we would have a large amount of this as in the protonated form. And actually, we have quite a significant amount in the protonated form, because if we look at another resonance form of this, where we bring this pi bond up onto the oxygen, oops, putting a positive charge at this site, this is actually now a quite stable resonance form. And what is it that's so very stable about this three-membered ring? Notice it's a three-membered ring. It has a p orbital on every single atom. It has a total of 2 electrons in that in those p orbitals. What does that give us the conditions for? It could be described as an aromatic ring. So just like the 2 benzene rings are aromatic, the cyclopropenyl cation is also aromatic. So this is actually the substrate that is undergoing the electrophilic aromatic substitution reaction, the nitration reaction. And so it's this substituent that we want to evaluate in terms of being an electron donating group or an electron withdrawing group to decide if it's going to be an orthopara-director or a meta-director. Okay, and because this has a positive charge, that certainly looks like it's going to be an electron withdrawing group, something that pulls electron density towards itself, and so as such it becomes a meta-director. So what makes it a meta-director? Well, after we make the NO2+, I'm going to abbreviate this mechanism a little bit. The nitric acid and sulfuric acid combine and lose water to form NO2+, which can get attacked by one of these 2 benzene rings. I'll just abbreviate one of them for now. I'm going to abbreviate that cyclopropenyl cation. It's going to form this sigma complex, which will have a positive charge. It's a carbocation intermediate, and of course that carbocation intermediate is always resonance stabilized. And when we think about the other positions that we can locate that positive charge, it is benzylic here. I'm sorry, it is allylic. This is allylic, so I can move this pi bond over to put the positive charge down here. And then it is still allylic, so I can move the pi bond once more. And I can move the positive charge to 3 different positions. As usual, we always have at least those 3 resonance structures for the sigma complex, so the carbocation intermediate. And notice where the positive charge ends up being located. It's either at this position. Oh, that doesn't look very good. Let's try a highlighter. It's either at this position, or this position, or this position. And where does it avoid? So these are the positions we get when we do a meta addition. Wrong pen. Sorry, I'm using a different tool than I usually use. This is adding to the meta position. Right, I added it to this meta, the position that's meta to the cyclopropenyl cation group. And when I add it meta, it ends up avoiding this carbon atom where we have this strongly electron withdrawing group directly attached. So this is the best carbocation intermediate. This is the best sigma complex we can get because we avoid those partial positives being real close to each other. Right? This positive charge is never immediately adjacent to this positive charge. So that's why the meta turns out to be better than adding to the ortho or para position. Okay, and then we finish our mechanism by showing any base at all coming in and deprotonating to give back our aromatic ring. And then we can deprotonate, I'll draw it as the carbocation. That's that cyclopropenyl carbocation. And now I have my aromatic ring back. And then we can deprotonate. Let me see if I can get rid of that. I'll just draw out this hydrogen, and then at the end we could deprotonate just with our A- of our strong acid, and we can go back to our neutral product. Our neutral product here, the carbonyl. So that explains, because it's a positively charged substituent on the aromatic ring, that explains why it's an electron withdrawing group and why it goes to the meta position. And you can go ahead and maybe pause this and see if you can select the response that you agree with. So first of all, can you explain how the observed regiochemistry for the reaction? So when we take a look at our choices here, hopefully you can see which one makes sense because we have this protonated substrate. We have the protonated substrate, which is which has this aromatic ring, positively charged aromatic ring that makes an electron withdrawing group and therefore a meta director. Okay, so what do you think about where our and then can you identify the structure of the observed dinitration product and explain why that's formed? Second nitro group is going to go, what are our choices? It can either go on the second ring at this position, or it could go on the second ring at this position, or it can go on the same ring as the first nitration, or we can actually, the dinitro product would have, maybe has para in both positions. So actually we're going to expect, for the same reason we just saw, we are actually going to get the meta product out. So D is not going to be likely because adding the nitro group to the para position would give a destabilized intermediate with two adjacent positive positive centers. So we want to look at A, B, and C as there are other possibilities. And now when we think about the reactivity of this ring, so let's imagine we did our first nitration, we'll get this product, and now when we go to add our second electrophile and we think about the reactivity of those two rings, we just added a nitro group. How does a nitro group behave? It is an electron withdrawing group. Does that activate the ring or deactivate the ring toward further reaction? It is now highly deactivated. It is a deactivator. So this ring is less reactive, and it would not want to add another electrophile. So this ring, so the second ring is going to be more reactive, and for the same reason, we still have our positively charged electron withdrawing group at this position. So it is a meta director. So we expect our second nitro group to come in to the opposite ring and to the meta position. So it looks like A has the right combination of the regiochemistry on which ring it attacks and the regiochemistry in terms of ortho, meta, or para. So what is our explanation here? The nitro substituted ring is deactivated toward further reaction, and the second nitration happens in the meta position the same way that the first one did. All right, very good. Thanks so much for joining me, and good luck on your problem solving.